So today I'd like to explain a little bit of a background about inductive types. So let me write a neat. There has to be a way to. They change this thing every once in a while. Nope, I failed. This black. Do you see black? That's black. Oh, I should be here. And I should be here. Let's say it's okay. It's annoying. Okay. So inductive types and the inductive constructions in general are important in various corners of mathematics and computer science, and they also feature prominently in formalized math and proof assistance because they unify a bunch of ideas. So once you implement inductive types in a proof assistant, you get a lot of functionality out of them. And rather than just hacking away with inductive types in Lean, I would like to say a little bit about the mathematical backgrounds and the ideas that we're trying to capture here, so that you can, I think, you can get a better overview of what's going on. There are some short notes here in the course lecture notes that can serve also as a sort of an overview. Morning. Okay, so what's the idea? So the idea is that quite often in mathematics, we build mathematical objects in a particular way. The particular way is as follows. We have some basic cases, basic objects, and then we have constructors. Let's call them constructors. These are operations which build new basic objects for new objects from existing ones. So build new objects from existing ones. And there is usually a proviso which says that this has to be done inductively. And we would like to understand what that actually means. If you read books, various books, you might get troublesome explanations that don't really explain anything. And today we'd like to make sure that we understand what this is supposed to be, mathematically speaking. But let's first look at some typical examples so that you know what I have in mind. So the first example, I think it would be a crime if the first example were anything other than the natural numbers. So natural numbers. We have one basic object, namely the number 0. This is a doctoral course, so I do not have to explain why 0 is the first natural number. When you were in elementary school, it was number 1. Okay, so, and there is one constructor, which is the successor operation. Another example would be lists. This one is more computer sciencey, but it's also quite common in mathematics, except there you might call them words or something, or finite sequences. And so now we have one basic object, which is the empty list, however you want to write that. Let's say like this. And then we have one constructor, which is called cons. Homework, figure out why it's called cons. There's a reason. And this one, the way it works is you take an element and the list, and you create a list which has this element as the head. So this is an element of your list. It's going to be the first element, and then this is a previously existing list. All right. And there will be various ways of describing this, like writing this down notationally, but this is how you can inductively generate all lists. You start with the empty one, and then you keep prepending elements at the beginning. You could also append them at the end, and then you wouldn't call that consing, you would call that snocking. I'm not kidding. I mean, computers, this is serious computer science, people. Okay. This is serious computer science, comma, people. Okay, there we go. Example, let's have one where we see that we don't have to have just a single constructor. So sometimes you're going to have several constructors. So for instance, something like 2, 3 trees would be like that. So these are trees that have 2 or 3 subtrees. So you would start again with an empty tree, but you don't have to start with an empty. Like, for instance, you could start with a leaf. So you say, now this time around, I'm just going to draw pictures. So a leaf is like a little dot. I don't know why it's not a leaf. Like, it's a leaf, but I draw it as a dot. So, okay, computer science. And then there are 2 constructors. So one constructor takes 2 trees. Let's call them P1 and T2, and it builds a tree. And the other one takes 3 constructors, 3 subtrees, previously generated ones, and it builds a new tree which has those trees as immediate successors. And you can tell that this is computer science because the trees are growing down. In mathematics, they grow up, but in computer science, they grow down. Why do they grow down in computer science? It has nothing to do with Australia. It has everything to do with the space on your page. If you grow them down, you don't have to guess how tall they're going to grow. But if you grow them the other direction, you have to know in advance how tall they are so that you know where to start drawing them. Okay. Let me quickly consult here. Blah, blah, blah. Okay. Yes. So what does it mean that these objects are generated inductively? So people will say things like, here's the first attempt. You might say, oh, we only need to generate finite things this way. We don't allow infinite lists or infinite trees. That would not be inductive. That is actually positively false, because we're going to have an example of an inductively generated set which contains infinite objects, namely countably branching trees. We'll have that in a moment. So that is just false, okay? You might try to weasel out of it by saying like, but in special case, they will be finite, la, 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 but you're just going to dig your hole deeper because I'll start asking what finite means. The other thing that you sometimes hear is they sort of try to say, you will only put in to this generation, in the inductive generation means that you're only allowed to generate those objects which you can generate using these constructions and nothing else. But that, I think, is completely circular and vacuous. I mean, what the hell, The infinite trees are also generated using only these constructions and nothing else. So that's not actually explaining anything. So we need an actual reasonable explanation of what we mean by inductive. And you can discuss these things using natural numbers, but I think more is gained by generalizing, because that forces you to say things correctly. With natural numbers, you can take shortcuts and sort of get sidetracked by philosophy in kindergarten. Okay, so let's see. Before we explain what inductive means, let us unify all these examples and also generalize them so that we're going to have a single general notion of what is going on. First, notice these are all trees. Well, the last example is very obviously trees, whereas lists and natural numbers are also trees. They're just kind of boring trees, because the trees in this case look like this. See how I'm doing math now? Because I'm doing numbers, I'm going upwards. Okay, so these are the kind of trees. Whereas with lists, what happens is that there is information in the node. So you would have the empty list, and then you would have a list that looks like this. Computer science again. Okay, so X, Y, right? And so on. Yes? So these are trees, but they don't branch much. They're more like bamboo shots or something. So the general idea is also known as well-founded trees. I'm going to explain why they're called well-founded later. Let's just explain what they are first. Okay, so you start with the signature first. You start with the signature that describes what kinds of trees you're going to have. Up here, we have three different kinds of trees, so each one would receive its own signature. So what does a signature look like? You have a set A of node kinds. You might also say node types, but that's slightly overloading the word type, especially in this course. So I'm going to call them kinds or sorts. They're just like colors. They're just some way of identifying which kind of node you have, or which kind of node you're forming. And then we have a map B, which to each A assigns its arity. Now, you might naively expect arity to be a number, but that's a very simplistic algebraic point of view that it's better to just say it's a set. And these are called branching types or branching kinds. Or just branching is also okay. So to each node, we assign a branching. And once you have this, you can now inductively, we still don't know what this word means, inductively generate some trees. And here we said, upstairs here, up here, we said, oh, the idea is that there are basic cases and then there are constructors. We're now actually folding both cases into a single one, which is just constructors. And we'll see in a moment how that works, but let me just write what it is. Given any branching kind little a and a map F which assigns to every element of B of A. Think of the elements of B of A as branch names. So up here you would have the branch names like left and right. And here you would have left and right and middle. You have to invent some names. Okay, so to every branch name, you specify what the subtrees are. So now we need to give a name to this set. So let's give a name to this set. I'm going to call it W for well-founded, A, B. So if I have A in A and I have F, which to every branch name assigns a subtree, a tree, we can form a new element, which we need some notation for it. So I'm going to call it tree, or it's better maybe let's call it no. Well, what did they call it in the notes? Bow. Okay, but where is it? Here, I called it tree. Form tree AF as a new element of WAB. Okay, so we have a single procedure. Let's see what this gives us in the examples that we just looked at. So maybe we don't give all the examples, but at least natural numbers I think we should do carefully. So how do we get the natural numbers this way? So you look at your trees and you say, well, there are two kinds of trees here. There are two ways to form a tree. You can have a tree that doesn't have any subtrees and it's called zero. Or you can have these other nodes which require a successor. So there will be two node kinds. So our set A is going to be two elements which just name what kind of nodes there are. So let me use symbols Z and S for zero and successor. And then the branching of zero is the empty set, because when you have zero, you don't want any subtrees. And then the branching for S is a singleton set, some kind of singleton set. So how about a star? Like that, because a successor takes one subtree, one natural number as an argument. And what will WAB look like when we start generating it? How do we even get started now? Because it looks like we don't have any base cases. Well, actually, you have base cases. When B of A is empty, when this set is empty, then you don't have to specify any subtrees. You just say, oh, there is a unique empty map from the empty set to wherever we're going. So we can use that one, and we just sidestep generating any subtrees. So the elements are going to look a bit like this. You will start with a tree whose node is of the kind Z. And now here you have to give a map. So you're going to give, I'm just going to write, like maybe I write O of WAB, where this O of WAB is the unique map from the empty set to the set we're generating. So everything, of course, is very self-referential and recursive, and while you're generating this set, you're referring to it and so on. So that's all super interesting. I'm just trying to understand what's going on. Okay, so what will the next one look like? Well, the next one is going to look like this. It's going to be a tree. You will say it's of the successor kind. If it's of the successor kind, I now have to give a map which goes from singleton. So it has to map singleton to some tree. So I'm just going to use the previous tree. So tree Z0. I'm not going to write all those indices there. Okay, and what will the next one be? Well, the next one will be a tree of type S, which takes star to a tree of type S, which takes star to a tree of type Z0. 1 close, 2, 3, 4, 5. Let's say it's correct. Okay, and so on. But you get the idea. Okay, so you could now also work out the other two examples, and of those, the more interesting one I think is lists, because it's more informative. So let's do that one. So lists. Now, to be a little bit more precise than what we did before, lists of elements from a given set X. So let X be a set. This is where we're going to take elements from. Every set is a set of elements. What I mean, there will be the elements of our lists. Okay. So now you tell me, what are the branching types? How many are there? Okay, we need a branching type for the empty list. Okay. How about all the other branching types? It looks like maybe there's just one other one, but that's a trick. It's not, because actually for every little x there is a branching type. So that's how you because that's how you label your nodes. You just create lots of node kinds. For each label you have one. So there are going to be lots of node kinds here. Well, as many as there are in X. So it will be something like E for the empty list, and then plus X, like that. What are the arities? Well, so now that I put a sum here, I need some way of writing down its elements. So how about computer science in left of E? So if I get this element, what is the branching? That's the empty list. It doesn't have any sublists. So this again should be the empty set. How about if I get an element here? So that will be a list whose first element is some little x. How many sublists should it have? It should have one sublist. And now by a process which is quite similar to what we wrote up here, you will generate lists. And you see how the node labels got encoded in A. You can work out the 2, 3, 3s. There will be 3 elements of A because there are 3 kinds of nodes. Let's just say what it will be. So the A will have 3 elements because it'll have one for the empty tree or the leaf, whichever way you want to start, and one for trees that have 2 subtrees, and one for trees that have 3 subtrees. And if you want to label them, then you will have to start multiplying by the set of labels. Yep. Okay. Let's have an example, a cautionary example that shows that things are not finite necessarily. And this is called the countably branching trees. We are going to have two. Okay, I'm not going to write A and B. I'm going to write again this the way you would do this as a normal human being. You would say there is the empty tree. So let's call this the set T. Okay, there is the empty tree. And given, so now I want trees that have countably many subtrees. So I'm not going to say given subtrees T1, T2, T3, dot, dot, dot. I'm going to say I have a function T from natural numbers to trees, like this. We can form a tree T. So what do these trees look like? Well, you start with the empty tree. Then at the next step, you can form a tree T, but all of its subtrees will be empty. So, well, depends. Okay, maybe I think there isn't a lot of difference between calling this one leaf or empty. So if I think, but it better corresponds to the picture that you picture that a leaf looks like this. And so then at the next one, you're going to have a tree which is growing an infinite sequence of leaves. And then at the next one, you are going to get a whole lot of trees because at each subtree, you can pick one or the other, whichever you want it to be. So sometimes you say, no, a leaf, but sometimes it's this gadget, and sometimes it's a leaf, but then it's, again, this gadget, and so on. So you're already getting uncountably many because you pick these, okay? And then you keep going, and then you're getting trees, like, you know, they go to some height like that. And each one of them is branching countably many times all the time, okay? Now, okay, so obviously not finite, but even more importantly, not necessarily of finite height, okay? So can you give me a tree that is generated like this, which is not of finite height? So let's do it in steps. First of all, do you see that this sort of thing can give me a tree of any finite height? I can have height 0, height 1, then I can generate height 2, then I can generate height 3. So for every natural number, I'm going to have a full tree of height n. Yes? But then I can generate, so let Tn be the tree, full tree of height n. So it's going to look like this. It's going to go countably many times, branch, 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 countably many times, branch, 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 and so on. And it's going to do this n times. I can do that. And then my tree is going to be like this. It's going to say the first branch has height 1. The second branch has height 2. Is this one. And then the next one goes one higher. So in general, I'll say that the nth branch is growing Tn. So now this tree does not have infinite height, finite height, because it goes above any given n in height. However, each single path through the tree is finite. You cannot go up forever. As soon as you pick one of these subtrees here, you now are destined to go, right? Okay? So that's why these are called well-founded trees. They have the general property that any tree going from the root to a leaf, any tree actually going from a root via nodes will end up in a leaf and will stop after finitely many steps. That's a general form, that's a general property that these trees have. And that would in fact be one way of specifying what inductive means, if only we already knew what finite meant. So we can reduce down to what is finite. But then when you try to explain what is finite, well, you still have some explaining to do, because you could say, oh, okay, let's describe finite sets. Oh, they are generated inductively from the empty set and adding one more element. Well, that's a circle. So we need some other better way. So what is another way of specifying what inductive means? Well, let's see. I'll make one philosophical comment, and then I'll do math. I think you're destined to fail to explain what inductively generated means if you only refer to the object that you are trying to generate. You have no chance of explaining what it is. For instance, piano arithmetic does that. Piano arithmetic attempts to describe what the natural numbers are by describing only natural numbers. It fails miserably because it does not actually describe the natural numbers uniquely because they are non-standard models of natural numbers. So, something's going on, and you could try to blame various people and branches of logic and stuff like that. For instance, I personally like to blame first order logic and say, like, this is completely unsatisfactory because what do you mean the induction principle is a schema that just has a bunch of formulas in it? So you can have a discussion like that, but the point remains that what is generated depends on the ambient. The richer the ambient, the more you can generate. Some empires were able to generate pyramids, and others were not, right? Because they were richer. So if you live in a richer ambient, you will generate more. Also, your ambient may have very special rules about what can exist and be generated, and that is also going to influence the objects that you're trying to generate. If your universe says everything is computable, rest assured you will not generate a non-computable countably branching tree. So there's that. So I think the correct way for me personally, and as a teacher, I'm just trying to brainwash you, is to always think about what is special about the object that you're trying to generate in relation to the ambient in which it is to be situated. That's the thing to answer. Well, we are now half a step from falling straight into category theory, because the answer then very obviously is going to be it is special because it has a universal property that no other object has, or to put it more correctly, every object with that particular universal property is the object that we're looking for. With that said, let's do it. Okay, so that's going to be a little bit of category theory. It's not very complicated category theory, and it's kind of satisfying. Okay, so there are a couple of steps. So given a signature, that's a very strange S. Signature A and then B from A to set. Of course, I'm using set here, but true category theorists would say, no, you can use a category C, which is good enough. That's just technique, okay? So given a signature A and B, then we can now define what we mean as follows. We will first define what it means to have a single step of generating. And then once we have the single step, we will explain what it means to complete that. So define, this is called, so a functor. Oh, it's so good to be in a doctoral course, because then I can just say functor and go on. Okay, P A B, that's a functor on set, which takes a set X and it gives the following sum. The sum ranging over A in A, X to the power of B of A. So a typical element looks like this. It's a pair of a little a and a function f, and this function f goes from B of A to X. There is nothing recursive about this. It's just a single step. Okay? Exercise, what does this functor do where, with maps? What is its functorial action? Okay, exercise. It does something. Why is this a single step? Well, it's a single step because it says, hey, we don't know what we generated so far or where we're starting from, but here's how you get a little bit more. Because this pair, if I wrote 3 in front, would be exactly the kind of single step that I was describing up here. See, up here, I was describing something, right? And this was like a single step, but it already closed the recursion. It already was trying to generate WAB using WAB. Now I'm being a little bit more careful, as computer scientists would say, I opened the recursive loop. I unlooped it by saying, no. At the beginning, I don't know what is the end result, so I'll just stick an X in here and work with the general X. This thing here is a sum of powers of X. So that's this thing here is called a polynomial functor. That's the name people gave such functors, which makes a lot of sense. Okay, now the set that we're looking for, WAB, is the initial algebra. PAB algebra. Okay, so first of all, what is an algebra? So let's recall this, well, or learn one of those. A PAB algebra XH is a set X with a map H, which goes from P, A, B, X to X. Why is this called an algebra? Well, algebras are things, sets, which are equipped with operations. Those operations make elements. The ring of integers is equipped with addition. Addition makes numbers. It takes numbers and it makes numbers. Well, in general, that's what's going to happen. Now, what this is doing is it is magically encoding, well, not magically, just smartly, encoding many possible operations into a single one. So H is the structure map. It's called it encodes all the operations that your algebra has. So let me just show you how you can do that with a ring, okay? So if you have a ring R, well, then it has a 0 and a 1 and a plus and a times and say and a minus, okay? So all of these operations I can stick inside, like with a single H, which is going to look like this. It's going to be singleton 0. Let's give them reasonable names. Z plus O for 1 plus R squared plus R squared plus R to R. What does this operation do? If it gets Z, it returns 0. If it gets O, it returns 1. If it gets a pair of elements from this component, it adds them. If it gets a pair of components, from this component, it will multiply them. And if it gets an element from the last component, it will take the opposite value. And that's going to be my H. And I'm not going to write it down because I said it and it's recorded. But what is this? Well, look, this thing here is just r to the 0, and this thing here is also just r to the 0. This is a sum of powers of r. It's a polynomial in r. So this is a polynomial for some signature that you can work out what it is. It's going to have how many node kinds? 1, 2, many. Okay, 1, 2, and then r squared many, and r. Okay, many, but it's going to have lots. No, did I say this right? I probably did. I don't know. Yeah. No, I didn't, because these are recursive calls. 1, 2, 3, 4, 5. It'll have 5 node kinds whose branchings are empty, 2, 2, and 1. So 0, 0, 2, 2, and 1. So that's why we call these things algebras, because that's what algebras are. We are generalizing algebra. Now, what will be, so that's a PA algebra. So let's work out what it is in the case of natural numbers. Well, example, natural numbers. What was our P? So P, A, B, if you look at back at what that was, it's going to be the sum over, okay, so after calculating the dependent sum and doing some reasonable isomorphisms, it's going to be x to the 0 plus x to the 1. Because we have one operation that is nullary and one operation that is unary. So that's going to be like, let me start writing 1 for the canonical singleton plus x. So what is an algebra? An algebra for this function, for this functor, is going to be something that goes from PAB of x to x, or up to isomorphism. That's the same thing as h, which goes from 1 plus x to x, up to isomorphism. That's like 2 separate maps, because you get one map by looking at the first component and another map. So that's going to be like a map from 1 to x. So that's going to be an element of x, which you get by looking at where you send this one, and another map, let's call it G, from x to x, where then you could write that H is the sum of those two, the co-pairing of those two maps. So those two things, X and G. Okay, you can figure this out. This is like a little bit of type category theory, not too much. You can, by thinking about what this is supposed to be, you can figure out all the notation here. So sometimes people give name to these. These are sometimes called iterative systems and stuff like that, right? I think Dedekind wrote about them. So he have an initial value and you have a way of repeating, and the natural numbers are the initial such thing. What does initial mean? Initial means that for every PAB algebra XH, there is a unique map R from the initial algebra, which in our case is WAB, to X, such that some diagram commutes. That diagram says that R is a homomorphism. It says that it respects the operations or the operation. So how does it work? It goes like this. You have P of WAB to WAB. Oh, do we have, we need a structure map from WAB, which we don't have yet. So This one, we actually claim that this is an algebra, so there ought to be some structure map here. What is this exercise? And then you have PABX, which has its own structure map H. And then up here, we say there is this unique R, which exists here, such that the functorial action R, works. Okay, I left out a bunch of details here. Don't really want to get deeply into the details, technical details of this math. I want to explain what the ideas are. So you can like go on the internet and try to find some place where you will read these details. If you find the NLab, find then after that something else, because that's just going to make you read its NLab for the next 2 weeks. So, or talk to me, but you should also try to actually unravel these things by yourself, okay? So, and there's plenty of literature, I can recommend literature. Let's just stop to think whether we really solved the problem. Did we explain what inductive generation means without talking about inductive generation? Well, I think so, because what we're saying now is just that we have some structures. Those structures, we did not say that they need to be generated inductively, because we're talking about stuff like coproducts and morphisms, and those all have their own universal properties and so on. And then we just say that something has to exist uniquely. And so that's going to give us all the properties that we want. Now, it's very useful to work out what this is in the case of natural numbers. Because you will say, how do I get this R in the case of natural numbers? You will see that what it gives you is a recursion principle. So this R, the existence of R, is what we usually think of when we say that we define something by structural recursion. So that's a useful thing to work out what it is. Okay? Any questions? I'll tell you a little secret. So I said we really solved the problem because we're just using logic and coproducts and stuff. Okay? But in logic, existentials or can be defined inductively, and not arrows. So arrows are special and pies are special, and so can coproducts. So you kind of see that inductive generation, inductive definitions are really very basic. After all, if you start thinking about the language that we're using, say the formal language that we're attempting to use, which would be some sort of a formal system described by syntax, syntax is inductively generated because it's a bunch of expressions which are just trees. So in order to understand these things, you need to understand syntax, which is a kind of an inductive thing. So to my mind, you really have to go back to sort of pre-mathematical understanding. You cannot start doing formal math in vacuum as a human being. Maybe you can as a Turing machine because somebody gave you a program and I mean, you're just like a machine. But as a human being, I think you really need to go like all the way back to the kindergarten, you know, and this is where you learned how to count and how to write. And all those things are a foundation for your understanding of what the hell is going on. So that's just my idea. Okay, so we're going to have a break, and then we're going to look at how this becomes type theory. There is still a modification that we need to make because the R that we're getting here isn't quite the one that gives us a recursion principle. but in type theory, you need to make it a little more dependent. And so we'll see how that works. And then we're also going to play with lean to see how lean does inductive types. Okay, a break, 15 minutes. So come back in about 15 minutes. Okay, let's go on. Oh, before we go on, remember how I was saying that what is being generated depends on the ambient within which the generation process takes place? So our definition of what W types, oh, these are called W types, by the way, also. Our definition of what it means to have an inductive type, does it refer to the ambient in which it happens? Well, yes, because it specifies what WAB is by referring to all possible ways of having the same kind of structure, and it says it's the initial one. So it's definitely what you will get as a result will depend on what other PAB algebras there are. Right. So we are explaining what inductive means by referring to the ambient universe, the ambient category. And this definition, by the way, it's going to work in other categories. It doesn't have to be sets. It just needs to be expressive enough to have these polynomial functor business going on. And maybe even if it doesn't have completely arbitrary polynomial functors like that, often it'll have special polynomial functors like these. These are very easy because for these you just need finite products and finite sums, right? So very nice polynomials.
Do they have a special term for this?
Finitary, I don't know.
They correspond very well with the different kind of categorical algebra definitions you tend to do.
Yeah. So right, so we are referring to the ambient, and by switching the ambient category or the ambient universe or the ambient type theoretic universe, we may be getting different kinds of gadgets. And in fact, we can investigate this, for instance, by investigating such examples where you replace type with prop, and then something happens. Okay. Yes, so now what is going to happen in independent type theory? In dependent type theory, something has to be dependent, otherwise it's not a name deserving of the ambient. So what we really want to do is, you see, if you stare at what's going on here, the universal property tells you how to create a function that goes out of your inductive type. So it's saying, under certain circumstances, there will be a unique map R from my inductive type to some other thing X. I'm starting to call them types because we're going to do type theory now. What are the special circumstances? The special circumstances is that you need this H. So as soon as you explain what the H does, then you will have the R. And so we want to do the same thing here. We want to say, oh, okay, in type theory also, we want to explain how to make maps out of an inductive type, but they can be dependent maps, which means that this X here should be allowed to depend on the elements. Okay, that's the generalization we need. And to make it, let's work out how this happens for natural numbers, because I think it's clear there. You can see what's going on, and everything that's going on is going to be at least somewhat familiar to what you already know. Okay, so inductive types in type theory. I'm not going to explain the general schema of what's going on because it's fairly involved when you start working with these things. I could explain it for, like, you get something, but it syntactically looks quite different from what you actually use, because it's not user friendly if you have everything described in terms of these explicit signatures. So let's work out the natural numbers. Okay, so what is the universal property for the natural numbers? We're not doing type theory yet. We're now just doing the universal property according to our definition from before. And the reason I want to write it down is because I want to recognize it as something and then see how it relates to type theory and what happens. Okay, so first of all, what is going to be an algebra? So I need to say, for every h like this, right? What is the universal property in the case of natural numbers? For every h like this, we're going to have a unique map here. So earlier we explained that in the example of natural numbers, to have an h like this is the same as to have an h from 1 plus x to x, which was the same as giving one element and one function g. Okay, so this would give us, given a set x, an element x in x, and an element and g from x to x, there is a unique map from natural numbers to x. This is the one we called R, such that, and now we have to say such that this diagram commutes, but then we have to figure out what it means for this diagram to commute in terms of my x and g. So the diagram is going to look a little bit like this. It's going to be 1 plus n, because that's what my polynomial functor is. And then down here it's n. And then here it's 1 plus x. And here it's x. And this is the map little xg, the one that is induced by these two. This map is what you would write as 1 plus r. This map here is the map that is induced by 0 and successor. And then this map here is R. So in terms of equations, how do you figure out what this is? Well, you look at this corner and you say, if I take any element in here and I run around with it this way, it's going to be the same as if I run around this way. But there are two kinds of elements here. One is from this component and the other one is from this component. So that's going to give me two equations. What happens if the element is from here? If the element is from here, then when I go this way, it's still the element from here. And then it's mapped to x. So one way around is I get little x. The other way around, I first get 0 and then r. So the first equation is r of 0 is x. The second one is, what happens if I'm from here? If I'm from here, I take a natural number. So in one case, let's see, I will get natural number, then I will get the successor of that natural number. So let's say this is natural number n. I'll get successor of n and then r. So it'll be r of successor of n equals, okay? And now if I go this way, I will first get r of n and then g. So g of r of n. These are the equations. Well, as a programmer, I would say, okay, this is R, which is defined by a structural recursion. It's the recursion principle. We got the recursion principle. Well, to be more specific, people would probably call this primitive recursion. or for natural numbers. And they would also point out that in actual primitive recursion, this R could have some additional parameters, and this one is not allowed to have additional parameters. And they would also say that it's a little bit weird that G is not given N. But all of that can be solved because if your category is rich enough and has exponentials, you can squirrel away all these extra parameters by currying and playing tricks on your category. So I'll leave that for some other time on how you do that, but that's what it is. So it's really just primitive recursion. Why isn't it just recursion? Well, if it was just general recursion, that would mean we can make completely arbitrary recursive calls. However, here we're only making a recursive call from successor of n to n. So that's called primitive recursion. Okay, now, what would be the dependent version of this? Well, the dependent version would mean that I want R to be a dependent map. But then X has to be a family. So we would start with a family X from natural numbers, not a single set X, but for every natural number, I'm going to have a different X. And let me also at this point rename my X to P for educational purpose. No, I already had a P. Let's call it X. From N to set. So I have lots of natural numbers. And then I want a rule that tells me how to construct a map which goes from natural numbers to X. But now it's going to be like this. Right? Because it needs to be dependent. Okay. So, well, I still have the same sort of X and G here, except now because everything is dependent, they will be dependent as well. So the data that I want is, I still need an initial value, X, which is an element. But what is it an element of? Well, it has to be an element of X at the initial value. So I first give an element of X of 0. That's where X is going to come from. And then what does G do? Well, G has to kind of respect the successor business. So it's not just going to map from xn to xn. It has to map from xn to the x of the successor n. So G is really going to be a map like this. Given any n in n, it has to map not from x to x, but from x of n to the successor of x of n. Sorry, successor of x at successor of n. That's my data. And given this data, I will get equations which are like this. There is a unique R, which is in pi, and in n, x of n, such that, well, the first equation is going to be what happens with R of 0. What do we think R of 0 is going to be? Well, it's going to be x. Right? Okay, and then there's going to be another one about R of successor of n. And this will be, and now it's not just G of R of n, because G always has to be told what level it's working with. So it also gets the n. That's the n that somebody might complain was missing before. So we now get it. Okay, G of n of, and now the recursive call, R of n. Okay. So what did we get? Well, we got a dependent recursion principle. But a better name for this is induction. Because let us write down the type of this process. This is a process, let's call it ind n. Let's write down what goes in and what comes out. Okay? So, okay, so for a fixed x here, let me also script it like this, okay? It's going to be, because we could also have this as an additional parameter, but I don't want to get into universes right now. So let's just write down the rest. Okay, so it will take something from x of 0. And then, so this is my little x. And then it'll take this map G. That's going to be my G. And then it's going to give me R. And that's my R. And given this, I can now write down the equations. And let me just call this int here so that I don't go crazy. Okay, so int of x, and so int will take an x and it'll take a g, and then it'll take a number. You see, it takes x, it takes g, and then in this pi it takes a number. So if I give it 0, it will give me x. That's the first equation. So this is equation number 1, this is equation number 2, this is again equation number 1, but it's now written more like the way you would write it if you were a self-respecting functional programmer. So the other one is going to be int x g of successor of n is, I'm just copying this stuff here, g of n, and now instead of r of n, I have to write int x gn. So we get this kind of fancier recursion, which for some reason I'm calling induction. Well, why am I calling it induction? Think about the case where x is actually a proposition. Remember propositions, types? Propositions are those types that have a single element and so on. Okay, so if we read it in the logical reading, we would say, aha, given phi of 0, so phi now is going to be something that goes from n to prop instead of set. Phi of 0, if you have phi of 0, and now I'll write the logic. Well, if I'm writing the logical reading, then I will actually write it as for all. And then I will also write arrows as implications. What did I teach in the first year? I taught first years never to use the same bound variable several times. So how about we call this one m? There we go. Well, what did we get? We got the induction principle for natural numbers. So in type theory, both recursion and induction literally are the same principle. You can have fun with mathematicians who don't know type theory by asking them, what's the difference between induction and recursion? And they say, well, they're kind of the same thing. And they say, how precisely? And then you wait for them to invent type theory, and it's kind of a hard problem, so they don't. In set theory, for instance, what happens in set theory? Well, in set theory, you get the induction principle comes first. So you observe that there are certain sets which are well-founded, and they, or certain relations which are well-founded. There's plenty of them in set theory, and they have an induction principle. Why do you start with the induction principle? Because you must. Why must you? Because you're using first-order logic. So the only thing you can ever do is write down statements, logical statements. So an induction principle, you observe there is an induction principle, and using that induction principle, you can show that there exist objects built from what we would call a recursion principle. So, it also works out, not surprisingly. I mean, after all, set theory is good enough to do all of math. But here we see that it's really welded together into a single thing. And what I also find illuminating is that you could argue that this type theoretic business is actually better than the category theoretic business. And if you say that out loud next to a bunch of category theorists, that's just going to be nerd sniping, because they will immediately go and say, no, but we can generalize this so that it's even more general than your type theory. And then, they'll like forget to eat lunch and they'll do this. So it's a fun thing. Okay. They'll say, no, 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 what you did is just a special case. It's just a slightly fancier category and so on. Okay. Let's see how Lean deals with these things. So, oh, by the way, here we kind of calculated what the induction principle is going to be. And now you can do this for lists and for trees or for anything you like. And you keep repeating this story and you're getting some equations and so on. Proof assistants that implement type theory, also the ones at least that implement the inductive types, which will be all of the useful ones, they also generate suitable inductive principles. Koch and Lean generate them explicitly, while Agda does not explicitly generate this ind thingy, but it allows you to define your functions using this sort of 1-2 pattern here with cases. And of all of these, Agda is the king of inductive definitions. It has the most of them in a precise formal sense because it has inductive recursion, and that's more powerful than what I'm describing today. Okay, well, in Lean, you say, I want an inductive type. And then you give it a name. And then you say what the clauses are. You can also place it in some place, like how about it's in type. And then you say what the clauses are. And you say Z is one of them. Okay. And say S is another one. So this now corresponds to our definition of this is the signature. Okay, I wrote down the signature, but the way I wrote down the signature here doesn't look exactly like a polynomial functor with a and b, because we want to be humane and write down signatures in an equivalent form that is actually appreciated by humans. There is a nice exercise where you can just define inductive W given a type and b from a to type, where 3 for all a b of a to w a b to w a b, which is fine, but nobody is going to actually instantiate this to a special case of inductive types. Anyway, now that we define this n, actually what we can do is, well, we can start building things. Like, for instance, we can say successor of 0. And it says, yep, that's fine. But secretly, it generated a bunch of things. Okay, we said there is S as a constructor, there is Z as a constructor. There's something called none now. Well, no, that's not true. What? There should be a rec. Ind. What is ind? Nope. What's it called? N dot. There was something. There we go. It's called n.rec, the recursion principle. Let's see what is the recursion principle. Let's unfold it. Okay. It says, this is my X. It's called the motive. The motive, one of those. The motive. Okay. But motive sounds so much better with an F. Okay. So the motive is the family that we are eliminating into. That's my X. And then it says, if you give me a base case and you give me the induction step or the recursion step, then for any t, where did t come from? What? Where's t? Why isn't it? Oh, here. For any t, yeah, it's okay. For any t, you will get something in the motive of t. It's literally what we had a minute ago on the slide. How does it know how to generate this? Well, because there is a schema here, right? That you always use the same. You're always going to use the same thing here, which is you look at your constructors and so on, right? Now you can't do arbitrary things. I mean, you really have to follow this polynomial business. Okay, so where's this polynomial business? It's here. You have to follow the polynomials. You could try to cheat. So, for instance, you could say, how about if I try to have some other initial algebra? Well, then it's going to complain. So, for instance, this, by the way, is okay. Okay, so this is still just natural numbers, okay? But then I could start doing weird things and say like, how about if I go from here to Booleans, okay? So now it's saying it has a non-positive occurrence of the data type being declared. What does that mean? More or less, it means you don't have a polynomial functor anymore. What the hell do you have? We're not going to generate this. I'm not going to get too deeply into this, but there are good reasons why you don't want to allow arbitrary such types, because if you allow arbitrary such types, you can get arbitrary recursion, and once you have arbitrary recursion, also on terms, not just on types, then you can inhabit every type, including false, and that means that your type theory, while it might be a fun programming language, cannot be used as a logical system. So there are limitations here. Okay, let's see how it generates some other inductive principles. So inductive. Also, let's see how lean itself, oops, not that one. No, there we go. How lean, no, not. Oh yeah, okay. How lean itself defines NAT. Well, inductive NAT, where 0 is a NAT and successor of NAT to NAT. So it's just written in a slightly different way. It says successor given an n in NAT, you can have a NAT. So it's actually using all this stuff. It's no different from what we wrote. There is no magic behind it. So you literally implement the way you implement your proof assistant is you work hard to implement general inductive types, and then it's easy to get the natural numbers. It takes, I would estimate, if you want to implement natural numbers and lists in a proof assistant, like as primitive operations in your kernel, that's going to be probably equal amount of work than to implement general inductive types. You don't actually gain much because you will just be writing this very specific code that could be more general. So, no point in doing that.
Isn't that also something that if you have the naturals, you can define the W type or something?
Okay, so that's a good question. So the question is, are all W types generated from some basic ones? And the answer is you can generate a lot of W types if you have, wait, what do you want? If If you have the natural numbers, you can go a long way, but you can definitely not everything. So a good case always is, can you get countably branching trees? Okay, so that one is usually beyond natural numbers. Why is that? Because of proof consistency strength. Well, if you the counter to know the sort of comprehending induction principles for countably branching trees is like comprehending transfinite induction up to omega 1, up to the first uncountable cardinal. So that's a lot of power. Yeah, let's see how it generates some more principles. So let's try list. Nah, I cannot bring myself to call it empty. It has to be nil. Okay, so that's what the constructors were. I just typed in what we had before.
How does it know that? I mean,
how does it know?
What were you talking about earlier with it being an external operation versus being parameterized? Why isn't it bothered here at all?
Oh, here. No, I actually defined a parameterized thing. So if you ask it what is list, it says, well, what is the type of list? The type of list is type to type. So I am parameterizing it with X. If I didn't want to do that, I could say something like, okay, so first of all, I can do something dumb and fix this to Booleans or something, and then have lists of Booleans. I could have a section variable and say variable X, and then it would be an external parameter. But yeah, you can define inductive types which are parameterized by some further types.
Yeah,
that's allowed.
That's not what bothers me. What bothers me is this cons.
Cons. What about cons?
I mean, if you look at the signature of cons.
Okay. What is cons? Nothing, because it's in here, list cons. Okay. It's parameterized also. If you say what is its type, it's for all X type, X arrow.
But what you mentioned earlier is that the constructors have to be. I mean, the constructors of list would be for each element we have a constructor and so on. And
yeah. Okay, I see what you're asking is. What you're asking is, earlier we said that the signature for lists would have lots of constructors, right? So that would be like here having like a constructor for. Okay, so I can demonstrate this in case X is finite. Okay, so if you want to have lists of Booleans, say, then you could do it like this. Right? You would say something, well, you would have this. And now this thing here is isomorphic to list of bool. Yes. Yes. Okay, so let me just make a general remark. Okay, so here we see something that happens with proof assistance specifically. Mathematically, none of this matters. They're all isomorphic objects. They're all the same isomorphic algebras. And this is how you want to think about them when you're proving theorems in category theory. When you are using computers, you could always say, but it's all Turing equivalent to Turing machines. Why don't we use Turing machines? So there's a good reason, and that is that the activity that we are performing here is of a different kind, where we are quite sensitive to which particular isomorphic copy we have at our disposal. So that's my answer. You can play these games and you can think about, oh yeah, this is isomorphic to that, and that is very good to know, by the way, because that opens up your design space. You say you become aware of the fact that you can do different things. You can do the same thing in different ways, and then you get to pick which one would be the best. But sure, I mean, you can do this. Now, if X is infinite, then of course I can't do this, because I can't have like a literal infinite source code here, one for each element. And then I would revert back to this. Yes. So to answer your question, I don't know what you're asking, but I think what you're asking is the answer to what you might be asking is yes. The way to view these operations here is that they can take in additional parameters.
I mean,
they're parameterized operations.
My question is more so like how, if we imagine a slightly more complicated example of, say, a tree.
Yes.
Where it could take multiple copies of list as an argument and then also multiple x's.
Yes, sure. Yeah.
Trees.
Yeah.
How does it know to differentiate between which of the arguments of these functions are parameters and which are the actual, arguments of the operation in terms of looking at the exponent in the term in the polynomial function?
Okay, so multiple x's, multiple trees.
Is it just like the first n arguments that don't depend on the?
No, I can mix them up. So let me mix them up.
I guess all the ones without a constructor are parameters.
Okay. So is your question, how do we know what these things here are?
Yes.
Okay. So the answer would be like this. You go and you parse this stuff here. Okay. And what you really want the proof assistant to do, it needs to deloop your definition. Just like with the W type, I delooped it into the P. So what you would want here, you would first want to have your P. And you would want to write that P, and you would know that P will take extra parameters X and Y. Okay. So it'll be PXY. And then you need to look at this stuff and say, okay, so what will be these trees? And this here, okay, this P here will be something like I've now delooped it. So that's what the proof assistant will actually do. It'll actually say, oh, these things here, these are just the recursive, these are arguments which will be the recursive ones because that's how it's written. Yeah. And now I will see that these kinds of trees are the initial algebra for this thing. That's what will happen in the background, one way or another. So the answer is deloop. Actually, any recursive calls are like that.
Yeah.
You write your function recursively in Haskell. Secretly, the compiler is certainly going to deloop something because it's not going to have an infinite descent of compilation, right? Okay. So shall we let's have a look at the induction principle for lists. Oh, okay, we're kind of running out of things here. But let's just understand this. Okay, so what does the induction principle for lists say? Before you look at the induction principle for lists, let's say it. What is the base case? You have to know what to do with the empty list. What is the induction step? Given a cons xl, if you know what to do with L, which is the tail of the list, then you know how to do with the whole list. If you have these two pieces of data, then you know what to do with lists. So, is that what happened? Okay. We want to, X is the type of elements of our list. Motive is the thing we want to do. Okay. So this says, so the naming is a little bit like this. Normal people would not call this nil here would be called something like X0. Okay. Yeah, or X. That's what I called X here. No, it's a proof assistant. It's not ChatGPT. If it were ChatGPT, we could ask it to rhyme this, but so it's a proof assistant. So it just calls it nil. It's just a bound variable anyway. So if you know what to do with the empty list, and does this say Does this say you know what to do with composed list? Yes. If A is the first element of my list and A1 is the thing I do with the rest, no, sorry. Given the first element of the list, given the tail, which is unfortunately called A1 here, and I know what to do with the tail, I know what to do with the whole list. So it's generating the expected inductive principles. This is what type theorists did, like in the 70s and the 80s. Every decade brought more complicated inductive types. And as I said, the Scandinavians put all of that into ACDA, whereas other nations maybe didn't go all the way. So the French stopped short of induction recursion. There is a branch of inductive recursive coq, which I don't think it's maintained. It's probably pretty obsolete. Okay. Any questions? Otherwise, we're done here for today. So next Friday, no lecture because I have to go to some stupid meeting. But I would like everybody who knows what their project is, I would like to see an initial blueprint. Okay? Anybody who doesn't know what their project is or is not sure about what's in the project should probably talk to me in the coming week. The blueprint, you should not spend a huge amount of energy on the blueprint, but you should have an initial blueprint which sort of lists the steps. And then once you perform some initial experiments, you should enrich the blueprint so that it starts matching your code. Okay. For instance, I've now figured out finally how I want to program things in my PCAs. So I'm now going to go back to my blueprint and update it a little bit, and then I'll keep going. I'm ahead of everybody in the class project. You people should be trying to catch up with me. Okay.